Hello, today we will be talking about wastewater treatment plant energy analysis, and our group is Earth Gang, and it consists of myself, Brianna, and Eduardo, Luisa, Ray, Sebastian, and Tashi.
So during our analysis, there were a couple of problems that we were able to identify within a wastewater treatment plant. And some of these issues were the amount of resources needed, space, and power it requires to operate these plants. Nationally, wastewater treatment plants account for an average of 53% of municipal energy budgets. So 53% of the municipal energy budgets nationally are consumed by wastewater treatment plants. So it is clearly quite costly to clean our wastewater. Another issue that we found is that there are gases that are naturally being created during the treatment process that we are not taking advantage of. And we can actually utilize these gases rather than disregard them. And a reason why it's beneficial for us to capture these gases is because they are biogases. And there are now engines called biogas engines that run off of biogases, such as methane, which is the gas we're going to be focusing on throughout this presentation. So these are resources that we should be taking advantage of, but currently are not. So in order to tackle these issues, coming up with alternate power sources seemed to be quite beneficial and the route to go if we wanted to decrease the amount of power we were consuming. So there were two alternates we are going to be considering. One is the biogas engine, which we are going to be integrating the cogeneration engine, which is a type of biogas engine, and it will be using that methane that is produced naturally during the treatment process, primarily during the anaerobic digestion process, and it'll be using that methane to power the engine, which will in turn power the plant. Now please keep in mind that there are limitations and the amount of methane being produced is not always consistent, and we will be discussing that later in the presentation. Another alternate that we discussed are solar panels. We know that solar panels have become one of the more popular power source alternatives. So we also went ahead and are going to look into that and see how much it can help in decrease our consumption of electricity.
Hi, my name is Lisa, and I will be giving you some background information on wastewater treatment plants in general. And we will first look at the energy consumption and cost. So, in our research, we studied the wastewater treatment plants here in El Paso and found that the average energy consumption per month is about 893,000 kilowatts per hour. This made the average cost per month about $53,000. The figures to the right represent how much the total energy consumption does each component require. As you can see, the aeration blowers consume the most energy, which are then followed by the pumping system. When anaerobic digesters are introduced to the treatment process, you can see that the blowers consume less energy, shown in the figure at the bottom. Therefore, splitting out the energy consumption is more efficiently. According to the data we obtained from El Paso Water, we saw that the consumption varies throughout the year. Energy consumed is at its lowest during the summer and increases about 100 kilowatts per hour during the winter. So this slide will discuss the importance of anaerobic digesters. Besides decreasing the energy consumption of the blowers, digesters are essential to methane production. Methane is an important player in our project because it will be fueling a cogeneration engine that then produces electricity which will be fed to the plant. The figure shows a profile view of a digester with the floating cover. Primary sludge entering the digester must be kept at a temperature range of 30 to about 37 degrees Celsius. This is important for the production of methane. You can think of a digester as the stomach or intestine where it breaks down or digests the contents. And as a result, it creates gas. In our case, it will be methane gas. The floating cover is normally preferred So there is a constant adjustment to the gas pressure inside as the gas is being produced. Fats, oils, and grease, also known as fogs, are recommended to be used in the digester as well because they increase the production of methane. This will help us meet the quota of methane to produce enough energy for the plant. These fogs can be collected from nearby restaurants or kitchens. As a side note, it's also beneficial to collect or prevent fogs from being disposed of in sewer pipes to ward off pipe corrosion.
Hello, my name is Eduardo, and I'll explain the justification. The main vision is adapting wastewater treatment plant to use alternative energy sources that will hopefully become a trend worldwide that can help any location save money on power consumption as well as carbon emissions. This main statement is supported by several other sub-points that support the main vision, or in other words, what justifies this idea. The first characteristic that supports the justification is money. It is clear that the amount of money to maintain a water treatment is considerably high. Wastewater treatment is an essential process, but it has a significant cost. It is clear that stopping or limiting wastewater process is not a viable option. It is indeed necessary to find alternative sources of energy. The second supportive idea is that a change is required. No matter the perspective it is looked at, it is clear that alternate sources of energy are necessary as soon as possible. This will of course reduce the cost and at the same time ensure that the desired results are equal or better at the time of producing energy than the ones already obtained with the current wastewater treatment plants. The last supportive idea is the amount of carbon emissions and the greenhouse gases produced by the electric company when energy is produced. Fossil fuel combustion for electricity generation accounts for around 40% of the overall nation's carbon dioxide, also known as the principal greenhouse gas. Additionally, it is known to be responsible for 67% and 23% responsible of sulfur dioxide and nitrogen oxide, respectively. The results of these pollutants have consequences such as acid rain or airborne particulate matter that leads to respiratory problems. Next, we will mention the results.
For the results, first I will explain to you what values we worked with to obtain these results. So it's important to mention that we brought this down to consumption per hour. We saw the previous values that talked about how much consumption there was in a month, and we also saw how it changes when you change it to hours, because overall the power demand is calculated by hour. So for instance, we talk about 3 levels of efficiency. An extremely efficient wastewater treatment plant should be around 800 kilowatt hours. Moderately efficient will be at 1,000, and an inefficient one should be like at 1,200 kilowatt hours. They scale up quite substantially with these values. And by also calculating these values, it helps us understand the fluctuation throughout the year. If there's a level of uncertainty of fluctuation, then you want to design for the most inefficient plant. But if not, then you want to design for the most efficient plant. And basically, whenever you're going to work with energy, the first step you can always take is retrofitting the wastewater treatment plant or any facility for that matter. In our case, for wastewater treatment, there are certain processes like an aeration that we can change the air pumps for those. When it comes to the cogen engines, they require methane gas. These cogen engines are also referred to as biogas engines. And in our case, we actually reached out to Clark Electric and they gave us these schematics for a very specific engine, which the model number is here, JGS312GS-N.L. And at 100%, it can produce 633 kilowatt hours. So what does that mean, right? So we can see how we have how much BTUs, British thermal units, it requires. Methane does have a conversion factor for BTUs. In fact, it's 1010. So by calculating how much BTUs the engine requires overall, which is partially electric and partially engine. So there's going to be some mechanical power needed and some electrical power needed. And we calculated that, which was 7,696 divided by 1,010, and we have 7.62 feet cubed, or meters cubed, because I understand that wastewater treatment plants also require to be in the metric system. So where do we go from there? We can't always assume that an engine will be working 100%, but in fact it can reach those levels, although a margin of safety is kind of required there. So I propose 3 levels: 100%, 75%, and 50%. I think anything below 75 is kind of unbelievable, but we're still going to show you those calculations for the sake of this project. At 100, if the engines work at 100%, then we're looking at different values of engines. Simply what I did here is divided the required by the produced, and it gave me the values. For example, at 800 kilowatt hour demand, with the 100%, you have 1.3 engines. For the 75%, you have 1.7. If you decrease the production, you increase the required. It's directly inverse. And then for the methane required, all I simply did, got the values of the engines and multiplied by the value of the required methane, which was in the previous slide. And you get those values on the right. Since we're unaware of which wastewater treatment plant we're working with here, we're, instead of giving a use of the methane produced, we are going to give a requirement of methane to show what can be done with what requirements. If a specific facility can only produce 10, let's say they can only produce 10 cubic feet of methane, then they can only purchase 1 engine. Therefore, that's how much power they can save with that. And these values aren't perfect, but that's because there's always that level of required redundancy. And if for a really good example, you can't buy 1.7 engines. Here it will be logical to buy 2 engines, but you can't buy 2.1 engines, and it's not logical to buy the 3rd engine because you're going to be overproducing. So there's definitely something that needs to be worked with. For the solar panels, this is where it got different. We selected 1 solar panel, and we saw how much 1 solar panel can produce. We found this website called PV Watts. It's a government website that helps you calculate the almost exact amount of power produced per year and month. And so on the right, you can see that results, and they give it to you monthly. I basically obtained how much it can produce in 1 year, divided by 12, divided by the days in the year, and an average amount of sunlight in that day, which in El Paso, it's 12 hours. These results are particularly specific to El Paso, simply because this is the city we live in. So now that we get those calculations, now we can interpret them to help us find the size or sizes of this solar farm. That value, 0.126 kilowatt hours, is the production that is set to be done here in El Paso with a panel that is promoted to have 0.3 kilowatt hours. Again, it's just depending on the conditions. Some places might actually produce more. Here, for instance, in our scenarios, which we have 3, we have different amount of panels. So we calculate from required power to required panels. These panels then can be taken to a provider. But to kind of ask for it in a more accurate way, you ask for a farm based on the size of kilowatt hours required. not based on the quantity. You can also ask for quantity, but technically different providers have different outputs. But focusing on our model, which is that LG model that is mentioned, I can give you that size. So the production required is given under farm kilowatt hours. That you can take to any provider and you can actually obtain their sizes and their values and their prices. But focusing on just this specific model, we can actually get the size of the lot that we require. The way we did this is basically by getting the area required per panel. We created an array that has 20 panels, and then we calculated the amount of arrays based on how much kilowatt hours one array can produce. And at the far right, you can see that we calculated in acres. And there you have the size of the lot.
Hi, my name is Ray Polera, and I'll be talking about the recommendations that we gathered from our project. Of the two options, we found the code generation engine to be the more preferable solution. We found it to be very resourceful. It makes use of the existing material, such as methane and the fats, oils, and greases in the surrounding area. It puts them to use and doesn't let them go to waste in landfills or the atmosphere. We also found it to be very efficient, and as seen in the previous slides, can easily balance out the high energy demand that a wastewater treatment plant requires. It is also very practical and can be implemented into most plants through retrofitting. If not, a few adjustments can be made in the process to enable this feature. For solar panels, we found it to be a viable option, however, it is just not there as an emerging research focus. For one, it is highly dependent on surface area. This results in higher startup costs from buying the panels themselves, the wiring and infrastructure necessary to run them, and the land acquisition required for the panels. The benefits also highly vary on the location. Some areas simply do not have the amounts of sunlight necessary to make this a viable option. A place like Seattle does not compare to El Paso in terms of solar panel effectiveness. For future research, we recommend looking more into the code generation engine option. Research can be done to make this a staple in future treatment plant designs and streamlining the system to increase its efficiency. Also, more transparency research should be done on existing cogen facilities to pave the way for more plants to retrofit. This is especially important in a cost analysis way so that more plants can be persuaded to convince their cities and client base on implementing one for themselves. For solar panels, a lot of research is currently being done already on this emerging technology. For our purposes, we'd recommend finding a way to reduce the area required per watt, whether this means making panels more efficient or creating a system with 2 layers stacked on top of each other, maybe with mirrors or something. The ideas are almost limitless. Another point of research could be simply to make them more cost effective through mass production means or other sorts of means. Different treatment systems could also use more research in general, specifically breaking down their energy usage. Transparency and statistics could be key in optimizing processes and finding solutions to fit the specific plants around the world.